for 3 particles. So 1 particle couples to another 2. And today I will talk about this hadron scattering. That's 2-body to 2-body. But in resonance energy region, at present for hadron scattering, no very solid, good theory from QCD. It basically is most commonly used is by meson exchange, hadron exchange, T channel exchange, and S channel, U channel, such thing. And the most important one is like meson exchange, T channel exchange. Of course, there are also some, if you have resonance. So the basic ingredients is still just this 3-particle effective coupling, as we introduced in last 2 lectures. So you can calculate this interaction. And today I will talk about exotic hadron-hadron S-wave interaction. Since in my first lecture, I showed that for most newly observed exotic particle, they sit just close to some threshold, so behave more like a molecule. So today I will show you from pi-pi scattering how this hadron-hadron interaction in S-wave may produce resonance and also maybe bound state. So today I will introduce this hadron-hadron S-wave interaction. First, I will introduce pi-pi S-wave interaction. So why we are interested in pi-pi? First, the pi-pi is a fundamental strong interaction process and a necessary input for many reactions involving multi-pions. Now, for the most hadron processes, the pion is involved in the final state. And for any multi-pion final state, you need to consider pi-pi interaction. And especially the S-wave interaction is important. And also, the isospin 0 pi-pi S-wave has the same quantum number of vacuum. That's 0 plus plus of F0 resonances, which include the sigma. Now it's called F0 500, and the sigma model, sigma exchange for NA interaction, and also the lightest global candidate, like F0 1500 or F0 1700. 1710. If you claim any F0 resonances, it couples to pi-pi, and you should more or less have some reflection from pi-pi S-wave scattering. Since if it coupled to pi-pi, it can go through this S-channel resonance like this. So it's very important to study pi-pi S-wave. And also the pion is the lightest hadron, and is besides the nucleon, is the most studied hadron. And for the F0 resonances, in fact, it's time dependent for the well-established F0 resonances. When I first entered this field, that's in the year of 1992, in the PDG, it listed 3 well-established F0. One is F0 980, and that's with width 46 MeV. And then F0 1300 with a coupled to pi-pi nearly 90%. And then another F0 1590. And after 4 years, the PDG changed. First, for F0980, it said the width is from 46 to 400. It's quite model dependent, and you cannot get this gamma equal to 46 anymore. And then the F01370 replaced F01300, and the couple to pi is very, very small. And then F01500 replaced 1590, and in addition, there is at that time called F0400 to 1200. So in 4 years' time, the PDG on F0 fully changed. These are claimed very established resonances. Still can change a lot in a few years' time. So it's even for very established resonances, you should be careful. In fact, the change of the picture can be explained by this. Previously, people know there is a narrow structure F0980, sometimes appear as a peak, but here is as a dip. Then if you look at this is a pi s wave amplitude squared, what later on we got. And this is corresponding to F0, original F01300, there is a peak. Then there is a peak F0 around 1590. But what we found is that instead of this, there is a broad background due to F0400 to that's sigma. And then only deep here appeared corresponding to the resonance, interfere with the background. So it's not necessary peak corresponding to the resonance. Sometimes if you have broad background, the deep, in fact, are due to the resonances. And this corresponding to F01500, and then another. So this, so there is no F01300 here. There is a F01370, but it couples very weakly to pi. They not show up here clearly. Okay.
So what is gamma this here from 46 to 400? I mean, for F0980.
For F090, yeah?
Yeah, so what happened to gamma in 4 years? It used to be 40. You told it is kind of model dependent result.
Okay.
Like it used to be 46, and then it became very big difference, 46 to 400. I mean, like what happened? The values of gamma for F0980.
F0980, 46 why it changes. I will explain later how all this changes. I will show you. And during these 4 years, I worked on with my collaborator, mainly with Professor David Bach. We worked on the pi s wave, and that's the plot, the final plot we got, and we conclude that first paper I wrote is F0975, a narrow resonance like 46 or not. We show it's not. So I will explain this, and then about this broad sigma to be here. And also from Chris Barrow, we found 1520. Now it's 1500. It's close. There's some error bars. And then this is 1370. At that time, we called 1365. And all these papers, we also reanalyzed the pi phase shift data. So I will show how these changes have been made. First, exotic pi s wave interaction. That's the broad sigma background with narrow resonance as dips instead of peaks. First, we show this is a pi. For the P wave, and the D wave and the F wave, okay. The background is very small. we can show only S wave is really important. And for rho and the F2, 1270, and rho 3, that's 3 minus spin 3, is okay. But for the pi S wave, there is a broad sigma. Then F0 980 sit here, F0 1500, and 3070 weakly coupled to this. And we reanalyzed the pi phase shift. What we got at that time is this. But in fact, there are similarities for pi, pi k, and pi n S wave scattering. If you look at the phase shift data, for the pi at spin 0, it looks like this. It goes up and a jump at F0 980 and it goes here. And for pi plus is negative, repulsive, like this from phase shift. And also for pi k, is in fact similar, slowly goes up and a jump. And for pi plus k plus is negative, repulsive. And for pi n and pi n isospin half, from the side they analyzed the phase shift. It also looks like slowly moving and then a jump. And for the isospin 3 half, pi plus proton is repulsive. So in fact, for this basic pseudoscalar and baryon, this nucleon, the lowest octet, they are quite similar. And the pi n, pi k, and meson, also these three very similar. Then, how to explain this? So what's the nature of the broad sigma? In fact, it's an important role for T-channel rho exchange for all these processes. If you use what I got for the rho pi just in that lecture, and you calculate this T-channel exchange, you will find for the pi scattering, for isospin 0, it's attractive, and for the isospin 2, it's just opposite sign. So one is repulsive and one is attractive, and the attractive force is 2 times of repulsive force. And for pi n and pi k is similar. For the isospin half, it's attractive, and for isospin 3 half is repulsive. You can do the exercise by yourself, just from rho exchange, and you project to S wave. This is very similar. And the phase shift is also similar. And for this, for the double charged channel with a higher spin is repulsive. And for the what we are interested in channel is attractive. So, and also the attractive force is really strong. And this, in fact, also noticed previously by Yiddish group. And this also studied by a Japanese group for this. So all reach this. In fact, for the meson, for this pseudoscalar scattering and for the pseudoscalar nucleon scattering, the rho exchange dominate. And some people used to use chiral perturbation theory to get low energy constants. But that one, if you get from T-channel rho exchange, it can give a dominant contribution to this CPT parameters. So it's basically people now agree that for this hadron scattering for this size is vector meson exchange, especially rho exchange dominate here. So the T-channel rho exchange can explain what I mentioned before. This behavior. This behavior, positive. This is due to T-channel exchange for this, and negative for this, yeah. So the Rho exchange is very important, and we just use this Rho exchange for the isospin 2. There is no S-channel resonance, so it's a T-channel dominant. So only T-channel is there, no S-channel resonance. That's the simplest. And the experiment phase shift like this, and then just with a repulsive force by T-channel Rho exchange, you calculate this by K-matrix unitarization, you can get this. So it's consistent with the lower energy. For higher energy, then there is a T-channel F2 exchange. You can make the calculation is attractive, so it goes up. So this T-channel meson exchange can give the natural explanation for this isospin 2 pi-pi scattering. And also then come to this inelasticity, the eta, this eta, how to call it? You know, for the scattering, there is a inelasticity described by eta, and then phase shift by delta. And for this one, if it's purely elastic, no open of other channel, then this eta should be equal to 1. But if we open other channel, then it should go down to be less than 1. And then you can, we just calculate this pi-pi to rho, and then to pi-pi again. And this can now move. Oh, good. So from here, this is a pi go to rho. You just use this rho pi coupling, calculate this kind of diagram, and to put it into this K-matrix formalism for the 2 channels, then you will get this. So this meson exchange works quite well for this pi scattering. The I equal to 2, that's only T-channel exchange. For both this phase shift and this inelasticity. So an important cause for hadron S-wave interactions appearing exotic is that the T-channel meson exchange amplitude has a comparable strength as the S-channel resonance contribution for S-waves. For higher partial waves, S-channel resonance contribution dominates. So it usually appears as peaks, not deep. Since previously I showed you, you see for the pi S wave, the rho appears a peak here, and then F2 appears a peak here, and this. And then here, in fact, it's also just a broad peak because it's too broad and provide a background to interfere with others. Then why broad sigma appears narrower in production processes than in pi elastic scattering? Sometimes, like for gypsite to omega pi and some other processes, you can see the sigma peak not as broad as in pi S wave. Why? If we use K-matrix formalism, the T is equal to K over 1 minus 0 K. If you expand, it's like this. And so the pi scattering is equal to this K matrix, you can calculate from row exchange to get this Bowen term, and then use this K matrix formula. This is I row is just a two-body phase space. Is for pi on share. Then this propagator will have this just a phase. Is for this loop diagram. If you only keep this imaginary part to keep the unshare part, so it's just a two-body phase space is I row. If you use the K matrix formalism, for elastic scattering is just this. And then for the production case, it's different. The first vertex is different from this. So it's like this. But for the final state interaction, they are similar. So just to replace the first by P instead of K, then you have this P over 1 minus I rho K. For example, for radiative decay, the gamma not interact with these two, and then the final state is just a two-body final state interaction. Then you get this P over 1 minus I rho K, like this. So they have the same denominator and the same pole position for pi, but for the first vertex, it's different. It's not K here, it's a P. So the production is not same as the elastic scattering amplitude. It differed by P over K. And the K we know that is basically determined by the phase shift, especially for low energy part, no in elasticity part. And the rho is a phase space factor. K is like this. And if you plot, for the pi S wave, if you plot T elastic scattering, it's like this. And if you for production, if you assume P equal to 1, it's just a constant instead of K. So you replace the K by P, then the production amplitude will look like this. So in the production case, you see the sigma appears lower and narrower. And in pi elastic scattering from this amplitude looks very broad. But in the production, you can show by yourself when you go back. Just plot this K and replace K in the numerator by P as a constant. You will get totally different picture. So in the production case, F0 980 here appears a narrow peak. And then the F0 1500 appear as a narrow peak. And yeah, so it's quite different. So resonance, especially for the narrow one, it's okay, sometimes as a peak, sometimes as a deep, and the width is quite similar. But for the broad one, is if you just take this width as a half of the peak, then it's very process dependent. For the broad resonances, its width is model dependent, process dependent. So you cannot avoid this. Then how about production vertex P? And in fact, this is the two. They give a general production process is like this. It depends on this. Not only depends on the pi invariant mass, but also depends on the pi plus pi minus energy. Usually, if this one, if the pi have very small total at rest system, it have a small energy, small momentum each. Then this dominate. You will have a peak. You will have this peak at a lower mass. But if you have this dominate, then you will have a sorry. Let me think. Maybe okay. Yeah, I made a mistake. This is basically times S. You will this is a so-called order zero. If sigma like this, and when you times this S pi, the first one basically is this, and is what called order zero. If you times by this, then it will drop this and goes up. So for the first term, it goes to higher, peak goes to higher. But for the if you have the second term only, this is negligible. Then you have no such factor. Then mainly depends on the this peak. You will have the lower sigma peak. So sigma peak position is process dependent, and this production P is a linear. You can approximation. You can use a constant plus a linear term of S. If this dominate, then it shift the peak goes up. If this dominate, it goes to lower peak and then looks narrower. So it's process dependent. And for example, for psi prime to j psi pi, this pi have very small momentum, small energy, and then it goes peaks at a higher part. But for j psi to omega pi, the pi have very large momentum, energy, single one. Then you have this no other zero for the numerator. Then you get this lower peak. Looks like this. So the sigma is process dependent. It's mainly the vertex. This production vertex is process dependent. They have the same denominator, but they have different numerator. It will appear differently in different processes. Then comes to the YF0 980's peak width is so narrow. And if you look at the peak or deep for F0 980, if you just measure this half, at the half of the amplitude squared, you get the width. Then it's well determined. It's about 46. Then the people, that's why originally they said gamma F0980 equal to 48 MeV. This is experimentally well determined. But the problem is, we know that F0980 can decay to pi and also couple to kk. And so it's so you can write this gamma F0 equal to gamma pi. If two channel, you usually add this width of two channel width. So the many theorists explain the nature of F0980 said because it's very narrow and it's coupled to pi, then gamma pi is smaller than, should be smaller than this, and have weak coupling to pi, not very strong. We know Zhou is have much broader width, but this is not true. And in fact, if you have this if you plot this, if G2, this coupling to kk is 0, if you plot this formula, amplitude squared, you will get the width more than 100 MeV for pi. So the width to pi is definitely larger than 100 MeV. If this resonance, if you take G2 equal to 0, you can plot this. But when you open its coupling to kk, you increase G2, then you will get this peak narrower and narrower. Not broader. So why? That's a if we take this as a m pi, usually we write squared root is this is a real part. Then take the imaginary part. And the if the resonance were above this relevant threshold, then it is true that the gamma total equal to gamma 1 plus gamma 2, and is just add them. And we know in this phase space factor, there is a k over s, and the k is a relative momentum of that channel, and the k is equal to k is equal to equal to this. When you get this this square root, you have plus or minus. How to explain? If in Riemann sheet, there is a pole here, and here corresponding to gamma 1, gamma 2 divided by 2I. But there is an additional in another Riemann sheet corresponding to, but from this sheet is go directly to here. But for another sheet, there is a gamma 1 minus gamma 2. It is need to go to, if you cut, this may be not so easy for experiment to student to understand. But this is go through the cutting point to reach this physical region. So usually this have no influence to the amplitude. But when you move to near threshold, and if this goes too far away and this goes to here, this is closer to the threshold, where gives a narrow width, but that's corresponding to gamma 1 minus gamma 2. And this real decay width is goes to far away. Let me see. This is from pole and the Riemann sheet, but it can also easily understand from this, just from this formula. From this formula, I use it. And I showed you that rho kk equal to from this formula, you can see if I take G2 equal to 0, I will get this dashed curve for G2 equal to 0. Then, if G2 is not equal to 0, GKK bar for when S equal to at KK threshold, this is 0. So at threshold point, this not changed. Should be same as this. But when the energy goes up, should be here. This threshold should be this here should be same. And when S is larger than threshold, this goes up. And then you have the amplitude squared will be smaller than this dashed curve. I think numerically you should be able to understand. This what you got is mf squared. The amplitude square like this. So when this formula is for the S larger, equal to so when this goes up, this denominator becomes larger, and this will drop. So for above threshold, the solid curve should always smaller than dashed curve from this formula. Yeah.
Why is R 4.21? Where do you get this value?
Okay, this is our fitting to this couple to pipe different channel. We can get this. For example, for GFSI to 5 pi pi, GFSI to 5 kk, and from this fitting to the data, we get this coupling constant. But no matter what value you used, no matter what the R, as long as G2 is not 0, then above the threshold, the solid curve should always smaller than dashed curve, and only at the threshold equal to this dashed curve. And when it goes to this smaller, this part, then you will get rho kk equal to so this I times this I will become positive. We are added to here. If you just plot it, first it will increase a little bit, but later on it also drops. So this near threshold coupling, this is so-called flat formula for this, will make this appears narrower. If you couple more strong to kk bar, it will becomes more narrow. So it's not like if you couple to another channel, decay dominant to another channel, it will become broad as usually, if this coupling is quite close to threshold. Only where above threshold, the decay to another channel will increase appearing width. So this structure width is different from this what you want to calculate gamma pi pi or gamma kk. As I said, the gamma pi pi is much larger. With this formula, with this very narrow width, appearing peak width, the gamma pi pi is more than 100, not less than 46. This is what our input here is already much more, is 150 or something. And it couples to kk. So I showed you the pole, one corresponding to gamma 1 plus gamma 2. And this one is in fact corresponding to the structure width is basically determined by this. You increase the gamma 2, will reduce the appearing structure width here. And because it's near this cut branching point, and if gamma 1, gamma 2, another pole goes to corresponding to 400. Our solution gives gamma 1, gamma 2 goes to 400. And the peak width, the pole for gamma 1 minus gamma 2 close to 46. So the structure width and this decay width is different. So and later on the PDG makes the change, not just determined by the structure width. And for theorists, if you don't understand this, you will try to have so narrow width to pi pi. It's very difficult sometimes not to explain it, but you should understand this. Now I also want to talk about the unitarity and the K-matrix approach. Relation among, I'm not sure whether you know this K-matrix or, okay. Usually, here I give the relation among S matrix, T matrix, and the K matrix. And I think most commonly used is T matrix, like the invariant amplitudes. But the S matrix is the origin of this. The relation with the S and the T is, this is only one definition. Sometimes you have different constant factor here. Then you just modify T by a constant, no problem. And so what we usually use is S equal to I plus 2I. Rho is 2 by the phase space factor and the T. And then you will get the T equal to K over 1 minus I rho K. And K is real. The unitarity relation is S, this S dagger S equal to 1 should be unitarized. And then from this, you can get this relation. And then the imaginary part of reverse of T is equal to minus rho. So this T minus rho, 1 over T, have a fixed imaginary part determined by phase space rho. And then define the K for the real part to be 1 over K. Then you get this K is a real matrix, and the T equal to K over 1 minus I rho K. You can always, from a T, you can always get the K like this. And from K, you can, if you know K, you can also get T and get S. For single channel Breit-Wigner resonance, the relation is that K is just the coupling constant over resonance minus S. Then you put this into this, you can get this T formula. It's just a standard Breit-Wigner formula. This is determines the width. And the S is just like this. So this is a relation between S, T, and K. Sometimes you may heard about if you add two resonances by two Breit-Wigner, it violates unitarity. You can show that if you add this, that it cannot satisfy the previous certify this relation. It violates unitarity. For a single channel two-body scattering, you can show by yourself. And then one can use the K matrix for the two resonances, and then like this, you will get a T. Then will satisfy unitarity. You can also use S matrix to be phase added like this. You get another formula. You can keep the same Breit-Wigner for this. If you with K matrix, then it's different from a single Breit-Wigner pole. But if you use this kind of unitarization, you can get the same as a single Breit-Wigner pole. So the unitarization scheme also gives a slightly different result if you use different unitarization approach. For multiple Hadron production final state, if you add this two simple Breit-Wigner, it's not violating unitarity. Since for the multi-Hadron production case, if you consider unitarity, you should consider the S matrix for multi-final particle is not two-body anymore. And then there are so many different channel coupled. If you only analyze one of them, you cannot, it's not violating unitarity. Only you combine it with other. So for multi-hadron production final state, you can hardly find constraint from unitarity. Since all these hadrons may interact with each other, you can just use simple Breit-Wigner or some, for the broad one, you introduce the S dependence of this numerator. But the S can be complex. You use this kind of thing to fit the data. Okay, maybe we'll have a break for 5 minutes, then I will carry on. Okay, we will come to the second part of this lecture. I will give more examples about this exotic S-wave hadron-hadron interaction. And just now is many years ago, from base observed a gypsite to gamma PP bar. They observed a clear narrow enhancement for the PP bar. And it may be claimed as a PP bar bound state, but it's not necessary to have a PP bar bound state. It can be other things like PP to PP eta, this reaction, and from COSY, they also observed the near threshold enhancement for the isospin 1 for the PP invariant near threshold invariant mass of PP. So it's the threshold enhancement may caused by strong final state interaction. We just shoot this equal to 1 minus IK rho. And for some opening threshold, no matter K is plus or minus, when you get amplitude squared, the opening of threshold will give if this is a constant, here increase at the threshold, this will just gives a reduction. So if it's very strong, then it gives a stronger decrease of the total T squared. So the final state interaction can cause, it's also possible, cause this strong drop, the near threshold enhancement. But at least it indicates the strong interaction, S-wave interaction between them. Whether it's repulsive or attractive, not known. And whether there is a bound state or not is also not so sure. Of course, the bound state can produce a strong such behavior. In fact, for gamma eta pi pi, there is we know there is a 0 minus plus around this range. And if it's coupled to PP bar very strongly, it may also cause such things. I will not go to details of this. And just for, we know for NN interaction, by 1 pi exchange, one can get this kind of things. And for the for the spin 0, sorry, maybe. Which one? For the, let me check. This spin, iso spin. This spin should be 110. Yeah. Oh, I get confused for this. It's for attractive for the deuteron. Deuteron should be this. And then you can have this deuteron bound state. And for NN bar interaction, this is for the pion exchange is negative. And then this one gets a biggest attractive force. And yeah, get biggest attractive force, and this may cause this.
But the 0, 0 and the 1, 1 cannot be in S wave to satisfy anti-symmetry.
Sorry?
Spin isospin 0, 0 and 1, 1.
Spin.
Cannot be in S wave. Otherwise, you don't satisfy the anti-symmetry of the observer.
Okay. Yes, spin 0. Yeah, spin 0 is antisymmetric, and this spin 0 is symmetric, and cannot be in S wave. Okay. Okay. This is but here is exchange and yeah. Okay. But only this factor is gives this. This factor. This one is for deuteron, one is dineutron. What?
Well, the 0, 1 is the
0, 1 is dineutron. Yeah, yeah. This is attractive, and for this.
yeah, it should be less attractive. Otherwise, you should dineutron.
This is repulsive of neutron. For spin 0, it's spin 1. Yeah, I need to think about it. You said for the neutron is isospin 1 and spin 0. Why you think for neutron? But this for dineutron is not only the pion exchange, but also exists other vector meson exchange. The binding is not purely due to pion exchange. But this factor gives this is correct for 1 pi exchange. Maybe for neutron, there are other meson exchange becomes important. Okay, but due to pion and the sigma rho omega exchange, this Ulich group also showed that can cause some enhancement for this. But this is, I agree, this is model dependent, since this low meson exchange, various meson exchange have some uncertainty. But one fact is that the final state interaction can cause an enhancement, near threshold enhancement. Whether it's enough or not, then depends on the parameters. Then about K lambda S wave near threshold enhancement. We know the lambda 1405 already showed in the first lecture that Kn scattering is predicted by Dalitz and Tuan in 1959 due to the like vector meson change. Many groups have made the calculation that they can form the bound state for K sigma and coupled to K lambda bar. Not K sigma, Kn can have the bound state. And also many people studied the K lambda bar and the K bar sigma. And we should, studied gypside to pk minus lambda and the pp to pk plus lambda at COSY. And here, the two processes have this k bar lambda interaction. And for these three but the final states, there are some interactions same and some are not. So it's good to check for this interaction from these two processes. And from base data, we clearly see the near threshold enhancement for K lambda. And divided by phase space, it goes up. And so it's something below threshold. How the here, and just the N star 5035 is just below this threshold. So it's possible due to this N star 5035 S wave is attractive also. And in fact, from other channel, K short lambda bar, there is also clearly near threshold enhancement for K lambda. That's we think is due to this N star 5035 is spin 1/2. And then in the same plot, there's another two peaks. One is N star 1875, another is 2080. It's just this one just below the K sigma star threshold, and this is if in S wave is 3/2 minus, and also here is just below the K star sigma threshold. So all these peaks appearing close to some Hadron threshold, maybe due to S wave interaction. So the S wave interaction may cause this some resonances, at least mixed with the resonances. And on the first day, I showed that even the proton have large 5-quark components, have this meson baryon, meson cloud model, or some multi-quark components. So and from the ratio of this N star 5035 to K lambda and to P eta, we can get the relative ratio of this N star 5035 coupled to K lambda to P eta to P pi, and it indeed have very strong coupling to K lambda, and P eta is even larger than its coupling to N pi. So this result supports that N star 5035 have large strangeness inside, and people previously already claim is a K bar sigma and the K bar lambda dynamically generated. So it's K bar sigma molecule components inside of this. And we checked when we have this big coupling to K lambda, then we should check with this PP to PK plus lambda. And we found that previous calculation by another group, Tsushima, Sipachev, and Thomas, without including N star 5035, they got this dashed curve. If we include this N star 5035 coupling, determined by this gypside, it just increase this part and fit the data much better. But then we got a message from Cyberchief that they said that they can fit the data without this star 5035. But we checked their data, like this dotted plot. From the dotted plot, we can see K lambda, this is an experiment dotted plot, and this is their fitting the dotted plot. Although they can fit the total cross section by adjust the parameter, but from the dotted plot we can see there is clear K lambda enhancement, but they cannot produce this one, although they can produce a total cross section. So in our reply, we emphasize that this indicates their model cannot fit the dotted plot. They can fit the total cross section. That's why the dotted plot provides additional information about this. We will not go through this. And also the Breit-Wigner mass of the resonance is quite model dependent. If you assume the only coupling to p eta or n pi, if you assume this is a constant width, then fit into the data, you get this. If you have the coupling to the eta n, use energy dependent phase space, then fit into the data, you will get 1535 and 150. This is used by PDG for Breit-Wigner width sometimes. And okay.
What is energy dependent phase space? Phase space suggests kinematically constant.
Yes. We know the decay width. We write like two-body phase space. This two-body phase space is 2K over S. And some people just use, so when you write this, even for this is a constant, for the amplitude, you use it's basically a constant. Then you still have this energy dependence. It's not especially like rho kk equal to so when the S, if you use this is quite energy dependent, near threshold. It's not a constant. Oh, sorry, how to say? The two-body phase space at threshold, rho equal to at threshold, rho equal to 0. For the width, at threshold, for the width, if you use a constant width, it's only a good approximation for the resonance well above threshold. Yeah, for near threshold, this one, for example, very close to rho eta threshold, and is below to K lambda threshold. When it is close to threshold, this width is strongly depends on the phase space factor, strongly depend on the energy. The width is proportional to phase space. when you write this width factor, the width is proportional to phase space. There should be a phase space factor inside. If you take it a constant, you assume the phase space is a constant there. That's only a good approximation for resonance well above threshold. So for the resonance close to some threshold, you must keep this energy dependence there. It makes a big change. Just like F0980, you cannot use a constant for the KK width. It's strongly energy dependent. So you must include this phase space factor. Yeah. Of course, if you use a constant, in fact, for this, if you use a constant, it looks like some solid line. If you use this energy dependent one, consider different channels. What you plot is very similar. The pole position, the 3 parameterization gives a similar pole position. But the width, the break, you use different widths. The Breit-Wigner mass is very different. For example, if you use a constant, the Breit-Wigner width mass is 15. But if you use this energy dependent for the eta n, you get this Breit-Wigner mass to be 1535. If you include another channel with this phase space factor, then the mass is 1400 and the width is 270. That's for the decay width. But the structural width, if you just fit this by constant, all 3 get very similar. This is what the experiment observed. You can get this width quite close to each other. But if you use Breit-Wigner, or so-called flat A for multi-channel fit, then this fitting parameter for the mass can be very different. Now, if you check the PDG, for many resonances, they will list Breit-Wigner mass and width, and the pole mass and width. Pole mass and width basically corresponding to the constant width parameterization, close to that, but not equal. You should solve this denominator to get the pole position. So the nature of 1535, as I introduced on the first day, it have a large SS-bar components, have large coupling to n eta, n eta prime, n phi, and k lambda, and weaker to n pi. Here shows some fit into the data, pi minus p to n phi and pp to pp phi. Include this n star 5035 with coupling can fit the data very good. And also for the K plus sigma plus, they also have similar things happened. That for the delta plus 1620 also have the by Zhou plus exchange can also form sort of bound state to produce the data quite well. So summary for our study on chip side to pk minus lambda and pp to pk lambda, that k bar lambda near threshold enhancement due to sub-threshold n star 5035 with large coupling of n star to k lambda. And this large component of strangeness makes it coupling stronger to strangeness and heavier. So n star 5035 is with a large strange content. And another point I want to mention is that sometimes, like for the amplitude squared, for the pi n from this J psi to p pi n bar, we found a clear near threshold enhancement. And this is, in fact, due to the subthreshold nucleon pole, like this. It gives a enhancement of this. So the near threshold enhancement is not necessary due to some new resonances. If you fit this by simple Breit-Wigner, you can also get a new resonance, claim a new resonance. But in fact, it's not necessary. It's due to this subthreshold nucleon pole like this. Then you need to use various form factor to adjust the pole to be same as the nucleon. Also, I found in PDG is sometimes very confusing, and sometimes they claim the A0 non-80 have large branch ratio to KK. In some paper they claim, and also F0 non-80 have large decay to KK bar, and like. So this 1850 have large branch ratio to P bar P. Then it's very strange. Since all the tails can couple, in fact, these resonances are below threshold. They for F0 980, when you observe it from pi, it sometimes have a narrow peak at here, about 980. And then the corresponding for MKK, it will looks like something like this. And sometimes the people just use the ratio to KK and they compare it to pi. They said, since this is very strong, just surprised by this phase space. If you added this, you claim the F0 980 decay to KK is larger than to pi. Is this correct or not, this statement? I think it's questionable. Since what we defined is should be at the peak, the branch ratio should at the peak position, the ratio. Then to KK is 0. So how you define the decay width for this? If you define it like this, then the nucleon, if you m pi n, if you check the nucleon tail for P11, then you can also make the contribution. Nucleon pole, just like here. When its mass is larger than pi n, it can also decay to n pi. So, how you say, do you claim that nucleon have large branch ratio to pi n? Its tail can goes to some open channel. So I think one should either change large to 0. Since all this is below threshold, then it cannot decay to that. You should use a peak mass instead of the tail. And although it cannot decay at the peak, but it has large coupling to this, and for above some threshold, it can go to this final state. And I noticed in PDG, sometimes they use this definition for the peak to determine the branching fraction. Sometimes they just follow some paper and then include the total integrated above this peak range. So you should pay attention. Sometimes they use different definition for the width, for the branch ratio. Then we come to the from the K sigma KP, like N star 5035 and the lambda 1405, we goes to hidden charm and hidden beauty. It's in fact a similar approach, just by vector meson exchange dominate, and basically rho is the largest contribution. And if K sigma have bound state and the KP have bound state, then you replace one light quark by charmed quark. Then you can also get this bound state. And this is why we go to this. And it's also with a different approach. Even for the rho exchange, you have different approach. You can use this, the simplest maybe K-matrix formalism, but that cannot form bound state. But another is like a Valencia approach. They used this one and assumed the propagator of rho is for S wave near threshold, it becomes a constant, Q square independent. Then you get this loop integration G. You can calculate this with some cutoff, and then with this we assume the Valencia approach. We can get this d bar sigma c will have a bound state at this end of the range. If you use more sophisticated approach like a E-bar model, then you should contain this Q square dependence to do this integration like this, and then it goes a little bit higher. And also recently we use a Ulrich-Bohm method. It's similar to this, but there are some details are different. We'll get like this. But we, no matter what kind of approach you used for this, the fact is that this vector meson exchange can provide a bound state. It's strongly attractive. And many other approaches tried different, and all reasonable model, we are sure that there is a bound state for d bar sigma c. And this is what we predicted for the d bar sigma c for the spin half, low risk is around here. And for 3/2, the low risk are 4418. And if you open the coupling to the light Hadron part, then it goes down to here. For the half minus is 4261, and the 3/2 minus low risk is around here. And they have some coupling to J psi n. And as you know, fortunately, LHCb observed the two pentaquark with hidden charm. It's just around our prediction. And one of them is 3/2 minus. And we can use more sophisticated this coupled channel. Ulrich Bohren, they studied for the K sigma and the pi n for light sector. They will just extend it to the heavy sector. And they for this D bar sigma C definitely have S-wave enhancement and bound state, and even have some P11 bound state predicted. And for the BB bar sector, there are more bound state to be discovered. This can be looked for at EIC. There, they should be able to produce such a heavy pentaquark with hidden beauty.
Is it believed that the pentaquarks are all molecules?
Sorry?
Are the pentaquarks believed to be molecules?
I think most likely in the molecule form. Since we also studied this with hidden charm with this compact one previously, and we found that they're simply not well controlled. That so many predicted much more than molecules, and then no observation. All the observations are very close to threshold, behave more like molecule. Yeah, so we.
It's different than tetraquarks. Tetraquarks, we don't know for sure.
For tetraquark.
This is pentaquarks.
Yeah, but for the tetraquark, most of them are also quite close to some threshold. Like Z sub C 3900 is close to D bar D star, and the 4020 is close to D star bar. All the very established one are are close to the to some threshold. Of course, we hope people can find this real tetraquark. Then you should find it not close to threshold, and in fact, if you compared our study of this pentaquark with hidden charm, with observation, you can always select some fits data perfectly, but at the same time, we have so many other states not there, and it's very model dependent. So, although we studied both configuration for molecule and for compact, and we more trust molecule. Yeah. Okay. Yeah. So there are more pentaquark with hidden beauty than with hidden charm. One should try to look for them. So now I.
What are you assuming for the carbon from the charm involvement? Is that some SU4 kind of symmetry, or just data?
No, here the heavy quark, C quark and the B quark, we just treat as a spectator. So we do not use SU4 or something. The Zhou coupling only to light quarks. Since in the B there is a light quark, and in sigma B there are two light quarks. The B quark is just a spectator. For the Zhou exchange, it only interacts with the light quark, and because the strength is similar, but this particle is much heavier, then it is more easy to form molecule. No. Since the Rho coupling to sigma B is similar to Rho coupling to sigma S. Since S and B here is just a spectator. Rho only coupling to the light quarks. So the Rho coupling to sigma C and sigma B and the sigma itself, they are same. Yeah, as a spectator. Of course, you may be some tiny modifications. But we assume the same. Yeah. Assume this heavy quark just a spectator. So now I come to the conclusion that so similar to deuteron, there are many hadronic molecules, and the most newly observed exotic states fit into this picture. Of course, they are, if they are close to some conventional hadron, then they will mix with them, and some may have very large components of hadronic molecule components, like X3782. It may be as a seed, they are CC bar, but then it mixed with this DD1 star, this molecule component. And recently we just published a review paper on hadronic molecules, and you can refer to this paper about these hadronic molecules. Yeah, thank you. Yeah.